Okay, thank you for the introduction, and I thank the organizers for giving me this opportunity of this talk. I'm going to talk about joint work with Yuji Odaka. So first, I roughly see a general idea on degeneration of varieties and compactification of moduli spaces, and then move to more specific problems. So first, let M be a moduli space of compact complex manifolds with canonical metrics. So here, canonical means Kähler-Einstein matrix. So we consider a compact complex manifolds which admits a Kähler-Einstein matrix. So we will later focus on a Ricci-flat case. So we consider a family of Calabi-Yau manifolds. And more specifically, we consider abelian varieties and K3 surfaces. And then we consider a compactification of the moduli space such that the boundary parameterizes degenerate objects, so degenerate varieties. So when you say a degeneration of varieties, there are several types, different types. So I show in this picture. So for example, in the first case, for example, we consider some equations in projective space, and if these equations have parameters, then we have a family of projective varieties, and then we consider a family of such projective varieties. And for a generic parameter, it is smooth, but the variety is smooth. But for some special parameter, it becomes a singular variety. So this is a kind of degeneration. But we also consider a degeneration as a metric space. So we consider variety which has a canonical metrics. Then for each family, we have a metric spaces. And then in this picture, this is a torus. So we may think of as elliptic curve with, so in this case, we have a flat metric in this torus. And then, so the torus becomes thin. And then finally, the limit becomes this S1. So here we fix diameter by rescaling. So the diameter is fixed. So the volume goes to 0. And then the dimension becomes smaller. So here the convergence limit means in terms of it's defined as a Gromov-Hausdorff limit. So for a non-collapsing case, in particular, if the Ricci curvature is positive, then these two types of degenerations are the same. It was proved by Donaldson and Sun. On the other hand, for a Ricci-flat case or a non-positive case, two types of degenerations can be different as in this picture. Okay, so the Gromov-Hausdorff distance is defined as follows. It measures the distance of two metric spaces. So we consider compact metric spaces. So let X and Y be compact metric spaces, and the Gromov-Hausdorff distance is defined in this way. So we consider some extension of metrics on unions, and then take infimum of epsilons satisfying these conditions. So in this picture, if X is this flat surface and Y is this surface with boundaries, then the Gromov-Hausdorff distance is like this distance. So and then we define a CMET1. So this CMET1 to be all compact metric spaces with a diameter equals 1 up to isometry. And so by a Gromov-Hausdorff distance, we have for each two metrics, for two metric spaces, we have a distance. So this has a metric, and this so this becomes CMET one becomes a metric space, and its topology is called the Gromov-Hausdorff topology. So we consider the following problem. So we have a moduli space M, and for M parameterizes some compact metric spaces. So we have, for each variety, we have a canonical metric, and by fixing diameter, so by rescaling, we have a compact metric spaces with diameter 1. So we have a map phi from M to CMET 1. And then we want to construct a compactification M bar and describe, and we want to extend the map phi to a continuous map from M bar. And we want to describe what the boundary maps to CMET 1. So if we settle the problem, then we know all the possible Gromov-Hausdorff limits parameterized by M. And we remark that this M bar may not be a variety. So M is typically a complex variety, but M bar may not be a variety. Okay. So there are some cases. So Odaka first considers a problem for the curve case, curve with genus G. So this the modular space is written as Mg. And in that case, the boundary parameterizes a metrized graph. This was studied by Odaka. And also he studied the abelian varieties case. So AG is a modular of G-dimensional abelian varieties with principal polarization. And in that case, the boundary parameterizes real flat torus of dimension less than or equal to G. And so he considered these two cases. And in a joint paper, we show that such the compactification of AG appeared in Odaker's work is isomorphic to Satake's one of Satake's compactification, and we apply the same method to K3 surfaces. So I do not go into the detail for MG case, but we just see the picture. This is a curve of genus 4. Then it deforms in this way, and then we have a singular curve with some node singularity. And these are called stable curves, and parameterized by a so-called Drinch-Mumford compactification. But if you if you consider the limit as metric spaces with diameter 1, then it becomes in this way, metrized graph. This becomes so this is a dual graph of this one. So each component of this curve as a metric space is shrink to each vertex, and then this node becomes very long and form the metrized graph. Okay, so next we briefly see the abelian varieties case, and then focus on K3 surface case. Okay, so for this is the abelian varieties case. So we consider all abelian varieties of dimension G, and L is a principal polarization. So we consider a family of such pairs and we define it to be AG. And via period, this is known to be isomorphic to this double coset space. This is a symplectic group, modulo unitary group, and this is a symplectic group with entries in integers. And in that case, the compactification considered is so there we have to add some boundaries. And in that case, so as a metric space, so this abelian variety is a torus. So this is a complex dimension G. So for as this is a real dimension 2G, and the metric is flat in this case. So the metric is flat. So this is a flat metric of torus of dimension 2G. Not all such torus appears, but some. As a metric space, they are all flat torus. And then as a degeneration, we have a I dimension of real torus, so the dimension becomes smaller. So the original one dimension is 2G, but for the degenerate one, we only have a dimension less than or equal to G. And these are parameterized by this double coset. So yes, this is so this degeneration is very simple. So this is an all flat metric. So this is essentially a linear algebra calculation, and we obtain such compactification. So we obtain such compactification and map to CMET1, which is continuous. So it is easy to see in this way. So the original abelian variety is as a metric space, like, for example, you can think of a direct product of S1, 2G copies of S1, and some of them shrink the diameter. So if we want the total diameter to be 1, then some of them will shrink, and some of the copy of S1 survive, and then we get the torus of dimension I. Okay. So okay, so in this AG picture, there appears so-called locally Riemannian symmetric spaces. This is locally called the local Riemannian symmetric space for a symplectic group, and this is for GLIR. So and there is a lot of compactification theory for locally Riemannian symmetric spaces, and we apply this. The one is called Satake compactification, which we want to explain. So let G be a semi-simple algebraic group over Q, and this G to be the R-valued point or its open subgroup, and K to be a maximal compact subgroup of G, and then we get the so-called Riemannian symmetric space. This is G over K. Okay, and then we take arithmetic subgroup. This is a subgroup of Q-valued points. So it is like a Z-valued point, integer-valued point of G up to a finite index difference. So and it becomes a discrete subgroup of G. And D mod gamma is called a locally Riemannian symmetric space. So a typical example is This has already appeared. For example, if you take sp2gr for G, and then maximal compact group is unitary group UG, and then we may take gamma to be this one, and then the obtained local Riemannian symmetric space is AG, the Ziegel modular variety. And Satake defined several compactifications of this of local Riemannian symmetric spaces in general. So to define Satake's compactification, we need another input data. So that is an irreducible representation tau of G. This is a complex representation. And then we take all Hermitian forms on V. So this is a real vector space, which we denote by W. And then W has a non-zero K fixed vector. And then we have a map from this Riemannian symmetric space to a projective space of W. So this is a real projective space by sending GK to this GW. This becomes an embedding. So we should assume that tau is non-trivial or not one-dimensional. So then this I becomes I is injective. I becomes embedding. So then we consider image of I and take a closure in this projective space. This is a compact space. But we, so this is in some sense compactification of D, but we want to define the compactification of D mod gamma. For this, we need to take some partial compactification between these two. So roughly saying, it's add irrational boundary components to D. So we do not give a definition, precise definition, but we can naturally define some intermediate objects, and then taking a quotient by gamma, you have a compact Hausdorff topological space. So we need some mild condition, but if this condition is satisfied, this quotient space becomes a compact Hausdorff topological space. This is not the induced topology from the restriction of projective space, but we can define some topology here to become a compact Hausdorff topological space. So we just give a simple example. Simplest example is in this case. So in this case, D is upper half complex upper half plane or unit disk. And then in that case, for any tau, ID bar, this is a unit disk with boundary. And then D star is a union of D with rational boundary points. So so the union of unit disk, open unit disk, and we only add boundary points whose coordinates are rational. Then by taking a quotient by gamma, you get this is a modular curve with a cusp. So gamma, in this case, gamma acts transitively on this rational boundary point, and this becomes a point. So this is a well-known compactification of modular curve. So we write this compactification as in this way, sat tau. So this depends on tau, and so there are several remarks. The boundary of this compactification is a finite union of locally Riemannian symmetric spaces of smaller rank. So there is such a finite stratification. And also we should remark that this compactification depends on the choice of irreducible representation tau. But most of them are actually isomorphic. So there are infinite many choices for tau, but there are only finitely many compactification up to isomorphism. So for many different tau, it becomes isomorphic. But it depends on tau. So there are several compactification, which is given in terms of root datum, but we did not go into the details for this. So the important case in our talk is the case where tau is an adjoint representation of G. So for any G, we have a natural action on Lie algebra. It's called adjoint representation. Then we apply Satake compactification for this adjoint representation for this Ziegel modular variety. And then we obtain this compactification. This is the same as one appeared before as a compactification using Gromov-Hausdorff limits. So yeah, so this AG bar is actually isomorphic to one of Satake compactification. So Satake compactification for adjoint representation. And for if you take another tau, for some certain tau, we have this compactification. This is called the Baily-Borel compactification. So each strata is a smaller Ziegel modular variety, and this compactification becomes a projective variety. It was proved by Baily and Borel. But for if you take adjoint representation, this is not a complex variety anymore. So this is just a topological compact Hausdorff topological space. Okay, so we just remark one thing, that if D is an irreducible Hermitian symmetric space, so if this D has a complex structure, as in the case of AG, the Satake compactification of adjoint representation is also obtained as a Morgan-Charlin type compactification applied to some or any toroidal compactification for AG. So there's another interpretation of this compactification. Okay, then from now we focus on K3 surfaces case. Okay, so we define K3 surfaces to be so in this definition, we allow AD singularity. So possibly AD singular complex compact surfaces with canonical boundary is trivial, and this condition. So for smooth K3 surfaces, this H2 is isomorphic to the so-called K3 lattice. So U is so this is a rank 2 lattice, indefinite lattice, and this is E8 lattice with negative definite E8 lattice, and by this we get a lattice of rank 22. The signature is 3, 19, and we fix a positive integer D, and we define F2D to be the pair of K3 surface and primitive polarization of degree 2D. And to describe them, we fix a vector from this lattice, which is primitive, and lambda square is 2D. So this is unique up to automorphism of lattice. And we write lambda 2D to be the orthogonal complement of this vector. So this is this has rank 21 and signature is 219. And we define O tilde lambda 2D to be automorphism of orthogonal group of lattice, which fixes the small lambda, and then we restrict to this smaller lattice. And then it's known that by using a period, so F2D is isomorphic to this quotient space. So this is a subset of a projective space of complex dimension 19. And yeah, so the correspondence is given a Kesri surface. We can choose some. So so suppose X is smooth, then we have such a isomorphism, and the Chern class of L goes to small lambda, and then we take a holomorphic 2 form of X, then the period gives some element in this projective space. So by this correspondence, it is proved, this isomorphism is proved. And then this subset of projective space has a structure of a Riemannian symmetric space. And then, so this O plus 219 is some index 2 subgroup of O219. And this is also index 2 subgroup of O tilde. But anyway, we have such a description of locally Riemannian symmetric space. And we now apply the Satake compactification. So we have, so F2D is isomorphic to some locally Riemannian symmetric space. So we can apply Satake compactification and take adjoint representation as a tau. Then we get the following stratification for such a compactification. And this is a union of F2D, and boundary is, there are two types of boundaries, F2DL and F2DP. So L is a isotropic line defined over Q. So L runs over such isotropic line up to this O tilde plus. And P is an isotropic plane. And these are finite. So this is a finite stratification. So the interior F2D, this is a subset of defined as a subset of projective space. But if you choose a real part and imaginary part, then we get some positive different two-dimensional subspaces of this real space. And this F2D is a complex dimension 19, so the real dimension is 38. And F2DL is defined as follows. So F2DL is so this is L is a line, and L pop is so L pop is this is a orthogonal space, the vector which is orthogonal to L. So this is 19-dimensional, and we take a real projective space, and then Yes. So for F2D, this is a positive definite two-dimensional subspace. And by degeneration, it becomes a semi-positive definite. And one direction is isotropic. So this is direction L. And another direction is V. This is positive. So in this case, this is a semi-positive definite two-dimensional subspaces. And we choose a basis V, then we can describe it this way. And then take quotient by some discrete subgroup, arithmetic subgroup. And then we get this locally Riemannian symmetric space description. And this has a dimension 18. And this part, F2DP, this is just a point. This is an isotropic two-dimensional subspace. So Satake compactification of F2D has such structure. And now we want to consider a map from this Satake compactification to metric space. Okay. So first, the interior part, F2D, of which we have a K3 surfaces, polarized K3. We have a polarized K3 surface. So by Yav's theorem, we have a unique Ricci-flat scalar form on X belonging to the class determined by line bundle. Then we just attach a metric space coming from this Ricci-flat scalar, but rescale so that the diameter becomes 1. And for 18-dimensional boundary strata, we take a point RV. So this is a point in real projective space in the description of this previous slide. Okay. And for such V, we can define an elliptic K3 surface such that this fiber class belongs to L, isotropic line, and the period of this K3 surface is V plus I lambda. So we can show that we can construct such elliptic K3. So this is VV, this is P1, base is P1, and the total space is K3, and the generic fiber is elliptic curve. And then we can define a metric on this base space by this formula. So for a tangent vector to base space, we can define some metric by integration fibers. And such a metric is called MacLean metric. And this is appeared in the pioneering studies by Gross, Wilson, and Kontsevich-Soibelman in connection with mirror symmetry and SYZ conjecture and Gross-Seibert program. So we can define a metric on this P1 base space. Yeah, so then for a boundary point in here, we attach so this MacLean metric. So this is homeomorphic to S2, and we rescale again to so the diameter becomes 1. And for F2DP, so this is just 1 point for each P. And for this, we just attach a segment. So with a standard metric. This is just a unit interval. So we defined for each strata, we we attach a compact metric space, then so we have defined this map phi. And the conjecture is that this is continuous. And so we expect this to be is true. We partially prove this conjecture. One is that the union of this F2D and this 18-dimensional strata, if you restrict phi to this, then it is continuous. So in other words, this is continuous except for finite points corresponding to zero-dimensional strata. And also, it can be proved that it is continuous on the boundary. But it is not proved yet that if you take a sequence from F2D to F2DP, then it is so it is continuous along this F2D to F2DP. This is not proved yet. Okay, so we'll give a very brief sketch of the proof of this first statement. Okay. So we take a sequence from F2D, which goes to a boundary point in F2DL, 18-dimensional strata. So I mean, we take a sequence in this Satake compactification, a sequence from F2D, which converges to the boundary point V. So we have a sequence of polarized K3 surfaces. And so, okay, so by the definition of topology on this Satake compactification, the periods behaves in this way. The K class is fixed, so K class is always lambda, and the real part of period goes to infinity, and the imaginary part goes to V. But if you take a real line through this real part, then it goes to isotropic direction L. So this is a limit behavior of the periods here. This comes from the topology on this Satake compactification. And then we consider hyperkähler rotation of these xi. Then these three periods are interchanged and switched. And so this, in this way, so the period, holomorphic periods, the imaginary part goes to lambda and real part goes to V, and the K class goes to infinity and in this form. So actually, in this way, we can prove that in the neighborhood of this boundary point, we can define an elliptic, some elliptic fibration. So in this way, for sufficiently large I, we obtain such elliptic fibrations. And yeah, in other words, if we consider taking before hyperkähler rotation, this is a special Lagrangian fibration. And then for boundary point, we defined elliptic K3 structure, which we used to define the Macri metric. Okay, so in this so after hyperkähler rotation, so this holomorphic period lie in the bounded set. So this implies that this elliptic fibration is deforms, but deforms in some small bounded set. So there's a small perturbation. It's not fixed, but yeah, so it deforms in some bounded region. And the Kähler class, so by this behavior, by this limit behavior, this Kähler class goes to the boundary of Kähler cone. And we want to prove that the rich Kähler metricon here, K3 surface, goes to this Macri metric on the base. So there is a special case where this where this real part is a constant modulo L, and this Kähler class are in affine line. So this means that so the sequence approach. So this sequence is are on a fixed line, and also approaches. The direction is in some 20-dimensional slice. So in that case, this elliptic fibration is fixed, and then in this case, this convergence follows from a result of Gross-Wilson and Gross-Tosaty-san. So Gross-Wilson studied the generic case. The generic means this fibration has 24 Ivan singularities, and Gross-Tosaty-san proved this for a more general, higher dimensional case. But for K3 cases, at least this implies this special case. So for our purpose, in general, we need to show that we need to allow some small deformation of this elliptic fibration, and also so this Kähler class may not be in a fixed affine line. So we need to make the estimate uniform with respect to this variation of these lines. So this estimate means we use we need some a priori estimates of the solution of Monge-Ampere equation, which was done in the work of Tosaty and Gross-Tosaty-san. And we need some additional arguments so that the estimates to make the estimates uniform with respect to some variations. So anyway, this is way we proved the first statement of the theorem. For the second statement, we used the Weierstrass model of K3 surfaces. Okay, so now we consider the non-algebraic case. So the previously we considered polarized K3 surface, but now we consider Ricciflat Kähler K3 surfaces. So it's not necessarily algebraic or polarized, and up to we consider up to scaling and hyperkähler rotation. We define to be the moduli to be MK3, and this is by period. This is isomorphic to this local Riemannian symmetric space. And again, we consider the Satake compactification of a joint representation. Then the stratification is given in this way. There are 6 boundary components. Each of them are locally Riemannian symmetric spaces. For example, this is locally Riemannian symmetric space of O218. And also for this case, we construct a map from this compactification to symmet1. So for interior point, we just attach a K3 surface. And for this MK3A, so this case is similar to F2DL in the algebraic case. We can define S2 with Maclaurin metric. And for this MK3B1, we take a flat 3-dimensional real torus modulo -1 multiplication. So for such a flat, so for such a 3-dimensional torus is parameterized by a locally Riemannian symmetric space of SL3R. And for this MK3C1, this is attached to 2-dimensional flat torus modulo -1 multiplication. And for other strata, we attach segments. And our conjecture is that this phi is continuous. And this conjecture we also partially proved. And this the union of this MK3 and MK3A this is continuous, and also the closure of this one. So this line, this edges indicates the closure relations. So the closure of MK3A, this is a union of these 4 strata, and this is continuous. So the proof of them is similar to algebraic case. Okay, so I think the time is now over. So yeah, I stop here. Thank you.